We talked about two different ways to remember the order of the provinces. The first one is crunchy peanut butter VA, where the crunchy stands for coastal plain, the one closest to the Atlantic Ocean, and then moving to the west you have peanut, Piedmont, butter, Blue Ridge, VA, you have the Valley and Ridge for the V, and the A for Appalachian Plateau. The other way we learned to remember the provinces of Virginia was with our hand. So if you do here, thumbs up for the coastal plain, because that's the province that we live in, that's the best. And then here you have your pointer finger. Pointer starts with P, and so does Piedmont. The next one up is your middle finger, which is your tallest finger, as is the Blue Ridge province. And then you move into the Valley and Ridge. So you go here and your finger goes down. Your ring finger goes down into the valley. And then finally, the last province is a little tiny province in Virginia called Appalachian Plateau. And so your little tiny pinky finger stands for the Appalachian Plateau. Coastal Plain, Piedmont for pointer finger, Blue Ridge for the highest elevation in the state. Then you go down into the Valley and Ridge, and then you have the smallest province, the Appalachian Plateau. Looking at the exit ticket data, almost all of our students did a really good job on question number 1. What number represents the Piedmont region? That's the second from the east is the Piedmont region, number 2. The second question says, between what two regions does the fall line exist? And it's between the coastal plain and the Piedmont. Finally, the last question is asking, karst topography is associated with what type of rock and what region? And students are getting this overwhelmingly correct with the Valley and Ridge and the limestone. Let's take a look back here at the fall line. You see this white line here? This is a line going all the way up and down the East Coast, not just in Virginia, and it's separating this sort of flat plain area of the coastal plain with the soft sedimentary rocks from the upland igneous and metamorphic, more resistant rocks on the western side. So this is the Piedmont over here on the west, and then the coastal plain over here on the east. A fall line is a narrow zone that marks the geological boundary between an upland region and a plain. It's distinguished by the occurrence of falls and rapids where rivers and streams cross it. And this picture down here in the lower right is showing you a picture of Great Falls, Virginia. So if you've ever been there, you know that it has really strong rapids, and this is exactly where the fall line is in Virginia. Information that we worked on today. So specifically, the 5 characteristics of a mineral being naturally occurring, inorganic, solid, having an orderly crystalline structure, and a definite chemical composition. The next question on the exit ticket that students struggled with was this question here, question 7. The color of a mineral in powdered form is called what? Hardness, luster, streak, or reaction to acid. The correct answer for this is streak. Here you have a streak plate and you have a mineral. So the streak plate is a tile plate, and you're dragging the mineral across the streak plate. As you drag it across the tile plate, it's crushing the mineral up. So you're actually seeing the mineral in powder form on that tile plate, and you're trying to see what color the mineral is in powder form. Some minerals are the same color as they are on the outside, but other minerals are having a different color than they do on the outside. Let's take a look at the gizmo that you did in class today. So you had mineral samples here. You actually had about 26 mineral samples, and you were looking at the different properties that we use to identify minerals. So you see that you have appearance, and within appearance you were looking at the common crystal shapes, and you are comparing your mineral to these shapes like hexagon, cube, rhombus, irregular, rectangle, and pyramid, and trying to see which one you thought that it matched. Then you were also looking down here for appearance at the luster. Luster is the way that light reflects off of a mineral sample. So you have metallic, which that really looks like tin foil or something metal. Then you have glassy, pearly, and dull. Also, you have in your properties that you tested today, density. Density is really important. And so density is the measure of how much mass is being fit into a certain volume. So when you take density measurements, you have to do two things. You have to first put your sample onto a scale. And so you can see that this sample A is weighing 36.4 grams. But then after that, you have to figure out what the volume is. In math, oftentimes you are finding volume using a ruler, and you're doing length times width times height. But when you're looking at mineral samples, these mineral samples are really irregularly shaped. So we use a graduated cylinder, and we use the water displacement method. So we're going over here and we're placing this into the graduated cylinder, and you saw that that water just got displaced up, and it got displaced by 14 milliliters. So the volume of the mineral sample is 14 milliliters. Now, to calculate the density, you have to use a calculator. So here we are, and we're going to do density is equal to mass over volume. So the mass was 36.4 grams, and you're going to divide that by the volume of 14 milliliters. So you see that the density of sample A is 2.6 grams per milliliter. The next property that you looked at was hardness. So with hardness, we're trying to figure out how hard the mineral sample is. We're using Mohs hardness scale. It goes from 1 to 10. 1 is really soft, all the way up to 10, which is the hardest. So diamond is up at the hardest at a 10, and talc, which is a mineral used to make baby powder, is very soft. You can break it up with your fingers. That's down at 1. So to test this, first we look at the fingernail test. If you can scratch a fingernail, or if you can scratch the mineral sample with your fingernail, then it has a hardness over 2.5. If your mineral sample can scratch a penny like this one can, then it's harder than a 3.5. Now, if it can scratch a glass plate, and this sample is scratching it up, then the hardness is over a 5.5. And then finally, if it can scratch a steel plate or steel file, then that mineral sample has a hardness over 6.5, but we don't know if the hardness is a 7, an 8, a 9, or a 10. We just know that it's harder than a 6.5. The next test you looked at is streak, and streak is looking at the what color the mineral is in powder form. So over here, this white box right here, this is representing a white tile plate. And when you take your mineral sample and you rub it across a white tile plate, oftentimes you're going to get a color on the plate. This sample is too hard because sample A is harder than a 6.5 on Mohs hardness scale. It's not going to rub off on the tile. But say we look at sample C, for instance. When you rub that on this streak plate, it's streaking yellow. That means that this mineral in powder form is yellow. Sometimes the streak color is the same color of the actual outside of the mineral, but sometimes you're surprised and it's streaking a different color than the mineral is on the outside. The last test you did is the reactivity to acid test. So you're taking some hydrochloric acid and you're dropping it on the sample. So this sample is not reacting to hydrochloric acid, but you did have a sample that reacted, and it was sample D. So you see how it's fizzing up when you put the hydrochloric acid on it. That's letting you know that this is reacting with hydrochloric acid and that this mineral is made from calcium carbonate. So because I was out of the building today, I didn't get to go over notes with you, but you should take a look at these at home. They're attached to this video. One of the main things that you want to be thinking about is how do we define a mineral? A mineral is defined by 5 characteristics. It's naturally occurring. It can't be made in a lab. It can't be man-made or synthetic. It's inorganic, meaning that it's not made from anything that was ever alive. It's solid. It has an orderly crystalline structure, and it has a definite chemical composition. When you look at this slide, you see just how much oxygen and silicon there is in Earth's crust. There's 47% oxygen and 28% silicon. And that explains why the silicate mineral group is by far the largest mineral group that we have. Today at the end of class, you had an exit ticket, and question 10 on the exit ticket asked you what mineral group has the most rock-forming minerals. Minerals like quartz and amphibole and pyroxene, all minerals that are made up of with the same building block of silicon and oxygen. And the correct answer to this question are the silicates. The silicates as a group are by far the most, they contain the most rock-forming mineral. Let's take another look at those notes. Here's one of the slides that we looked at about igneous rocks. This is showing you that igneous rocks are created from molten material. Now, that molten material could either be under the Earth's surface in the magma chamber, or it could be erupted out of a volcano. Where the molten material is and where the molten material cools and solidifies has everything to do with what the igneous rock ends up looking like. Here's a good example of that from your notes. You see example A has little tiny dots in it. You can see all of the different little minerals in it. And that's because example A cooled inside the Earth in the magma chamber. It had a long time to cool because inside the Earth in a magma chamber, when that starts to cool down, it's like the minerals are inside of a thermos, and it's going to take years and years and years for that magma chamber to cool down. And the slow cooling really gives the minerals a good chance to grow out and to grow large. Whereas when you look over here at example B, you can't see any individual minerals. This is considered fine-grained. And so what you can infer from that is that this was erupted out of a volcano. This formed very quickly as it was erupted from a volcano. So how sedimentary, metamorphic, and igneous rocks are formed. Igneous rocks are formed from molten lava solidifying. Sedimentary rocks are formed, first you have to form the sediments. So they're formed through weathering and erosion of sediments. And then after that, the sediments are compacted together. They're pushed down because you have sediments put on top of sediments put on top of sediments when they're deposited in the ocean, and they get compacted down and squished together. If the sediments are small enough, like mudstone, they'll actually just compact into a rock just from the compaction. But some sediments like sand or like larger pebbles, you have to have like this matrix of like groundwater, and it has all these minerals in it that almost act like a natural glue. And then finally, metamorphic rocks are formed when heat and pressure are put onto already existing rocks. And we're talking about like large scale heat and pressure way deep inside of the Earth. Here's something else we spent a lot of time on today. Aphanetic and phaneritic. Now, aphanetic occurs when you have rapid cooling that creates small crystals. It's a fine-grained texture. This is an extrusive rock. Remember, extrusive is something that's exiting the Earth. So this is happening in the case of volcanic eruptions. Whereas phaneritic rocks, here on the right-hand side, they form from slow cooling. It creates large crystals because they have lots of time to form. It's called a coarse-grained texture, and this is an intrusive rock. Intrusive rocks form inside the... Now, I wanted to look over here because some students were asking whether or not pumice floats. So I wanted to give you a view of that. Here's some pumice right here. We're going to drop it into the water. As you can see, it definitely is floating. So if you get a side view, you can see that it's definitely at the surface and it's floating. Pumice is silica rich. Silica is low density. Now we're going to take a piece of scoria, which also has the same vesicular texture as the pumice, but you can see it's much darker. It's higher in iron, and iron has a higher density. When we drop this in, you could almost hear that. It just totally dropped to the bottom of the container. So the conclusion is that yes, pumice does float it out and see. So if we start first over here with the calcite, we're going to drop a little bit of hydrochloric acid on it to see if it fizzes. And if you look very closely, you can see fizzing action going on there. So it looks almost like you opened up a can of Sprite, and you can see the fizzing. So that's the calcite. Now let's take a look at this limestone right here. We're going to put a little bit of hydrochloric acid and see if it fizzes. Again, the answer is yes, that's fizzing quite vigorously. Now let's move over to the fossiliferous limestone. Hopefully you can see this on the camera. It might be a little bit too dark. That's a bit harder to see on the camera, but you can also maybe hear it's fizzing. It sounds like you're opening a can of soda. Now this rock right here, this marble, this rock is old. It's undergone a lot. So it's not going to fizz as rapidly as the limestone. But we'll see if it'll fizz for the camera. So you can see that. You see that movement there with the liquid? That is it fizzing, and you can also hear it fizzing. So the answer to this question, does marble react to acid, is yes. And the reason it reacts to acid is because limestone is the parent rock of marble, and limestone is made of the mineral calcite, which is a carbonate mineral. This is a mineral that has as its building block C. Alright, let's talk about a couple clarifications. Some students ask me, how are they supposed to figure out what the grain size was when they're looking at different rocks? So grain size in rocks can mean the size of the crystal grains or of the fragments. And so we say coarse grain is the largest, medium grained, and fine grained. With coarse grain, most of the rock is made of grains as large as a grain of rice or larger. So you can see that here with this igneous rock, and you can see that here with these sediments. Medium grained, the individual grains can be seen without a magnifier, but most of the rock is made of grains that are smaller than rice. So here's an example here of sandstone that is medium grained, and then here's an example of an igneous rock that's medium grained. And then the smallest is fine grained. Fine grained, the individual grains can't be seen without a magnifier or a microscope. And again here, you're seeing the metamorphic rock called slate, and this over here is fine grained sandstone. This on the right hand side are just fine grains of precipitation and precipitation of rocks. Last unit was our weather unit, and we talked about precipitation being rain, snow, sleet, hail, anything like that. This unit, we're also using the word precipitation, but a little bit differently. We're talking about precipitating minerals and precipitating rocks out of a solution. Here's a picture of the Bonneville Salt Flats in Utah, and you can see all behind the people, that's me right there, there's all salt flats as far as you can see. And this is an example of a chemical sedimentary rock. Here's another aerial picture here of the Bonneville Salt Flats. The Bonneville Salt Flats of the western Great Lake Desert were formed through the evaporation of Pleistocene-era Lake Bonneville. The salt flats are actually the bed of that once massive lake which rivaled in size to present-day Lake Michigan. The flats are composed mainly of potash salts ranging in thickness from less than 1 inch all the way up to 6 feet of chemical rock salt. In 1827, a trapper, trader, explorer, and frontiersman Jedediah Smith was perhaps the first white man to cross the Salt Flats in 1827 while returning from his first expedition to California. 6 years later, Joseph Redefort Walker, another trapper, mapped and explored the areas around the Great Salt Lake and crossed the northern perimeter of the flats while in the employ of Captain Benjamin L.E. Bonneville. It is from Benjamin Bonneville that the Salt Flats and Prehistoric Lake derive their name, although it's unlikely that Bonneville himself ever even saw the flats. In 1896, the area's first use as a raceway was conceived by publisher William Randolph Hearst in a publicity stunt. Hearst hired William Rischel of Cheyenne, Wyoming, to attempt a crossing on bicycle. Rischel completed the journey, but it took him 22 hours to cross the Salt Flats in 22 hours because they're so big. Early attempts to promote automobile racing failed until 1925 when Ab Jenkins, driving a Studebaker, beat a special excursion train by 10 minutes in a race across the flats. Since that time, the Bonneville Salt Flats have attracted racers from throughout the world and have become the site of numerous land speed records. Their attraction for these racers is due to the hard flat surface expanse in an area so flat that from certain perspectives, the curvature of the earth can actually be seen. Here's another example of where chemical sedimentary rocks form in a lagoon. You see this light blue area here? This is the lagoon that surrounds islands in the South Pacific. So chemical sedimentary rocks form in areas of calm, warm waters. And so this is a perfect example of this. These waters are so calm that there's hardly any sediment at all, and the waters are perfectly clear. You can see straight through down to the bottom. Here's another picture of that here, and you can see the coral reefs that are forming. They form in the same environment in that calm, warm water. Here's a side view of that. You see you have the open view, the open sea right here, and then the way that the sandbar is formed, it goes up here a little bit, so it sort of protects this lagoon area from any of this high energy open sea wave action that's happening. You can also see that the sunshine is beating down on the lagoon. That's evaporating the water out, and then you have minerals and rocks that are precipitating out of this solution and then falling to the bottom of the ocean. Eventually, if this were to evaporate totally out and you didn't have any water at all left, then you would have something that looks like the Bonneville Salt Flats. So this was once covered totally by water, but now all that's left are the chemical sedimentary rocks. The rock cycle. Any rock type, sedimentary, metamorphic, or igneous, can turn into any other of the rock types as long as it undergoes the correct process. So how does an igneous rock form? Well, first you have to have melting, and that melting is going to create magma or lava. When that magma or lava cools and crystallizes, that's going to create an igneous rock. So if a metamorphic rock melts, it's going to form lava. If that lava then cools and crystallizes or solidifies, that's going to create an igneous rock. If an igneous rock, an already existing igneous rock, melts, that's going to create magma or lava. And if that magma or lava cools and crystallizes, that's going to create a different type of igneous rock. If a sedimentary rock undergoes melting, that's going to turn into magma or lava. And if that cools and crystallizes or solidifies, that's going to turn into an igneous rock. So in order for something to turn into an igneous rock, first you have to have melting to create the magma or lava, and then that